Although we haven't learned yet how to solve differential equations, in other words, how to find that unknown function, if someone says to us, hey, I've found the solution, we do have a way of checking to see if they're right. That's what example 2 here is about. First, let's verify that the function n of t equals e to the 0.49t is a solution to the differential equation dn of t dt equals 0.49 times n of t. All we have to do is plug this proposed solution into both sides of the equation and see if we get a true equation. So in other words, we're checking that if I differentiate e to the 0.49t, I will get 0.49 times e to the 0.49t. So I just plugged that proposed solution into both sides of the differential equation. Now, I don't want to write this exactly like this because if I write this, I am asserting that the two things are equal, and we don't know that yet. So the standard way of saying, okay, this is a question, I'm not making a statement, is to just put a little question mark above the equal sign, and then we'll compute both sides. So on the left-hand side, using the chain rule, we have the derivative of our exponential function will be the exponential function times the derivative of the exponent, because the exponent was not just a plain old t variable. So again, I'm still asking myself, is that the same thing as what I have on the right-hand side? And let's see, the derivative of the exponent is 0.49. And yes, that is certainly equal to 0.49 times e to the 0.49t. So, yep, it's a solution. Let's now verify that 70 times e to the 0.49t is a solution to that same differential equation. So again, I'm just going to plug that proposed solution into both sides. And I'm asking the question, are these equal? Let's see. If I compute the derivative on the left-hand side, the 70 just comes along for the ride. The derivative of the exponential function is the same exponential function, but then the chain rule says, hey, because the exponent wasn't just a plain old variable, we have to multiply by the derivative of that exponent. And again, I'm wanting to know, is that going to come out to be equal to the right-hand side? So let's see. On the left-hand side, I have 70 times e to the 0.49t, and then the derivative of the exponent is 0.49. And yeah, sure enough, that is, except for writing factors in a different order, that's exactly the same as our right-hand side. So we have verified that that proposed solution does in fact provide a true or valid equation. Here are the graphs of the two solutions that we just verified. The first one is the graph of n of t equals e to the 0.49t, and the second one is the graph of n of t equals 70 e to the 0.49t. Notice these are both exponential functions. and that the population, as time goes on, grows faster and faster and faster. This is not realistic for most situations because usually there's going to be some sort of constraint on the growth of the population. In 3.6, we talked about this model, derivative being equal to a number times the function. In other words, a differential equation that describes a population whose growth rate is directly proportional to the size of the population. We talked about that leading to exponential growth, which is what both of these graphs are showing us. Again, most populations will not grow like this. Usually there are limiting factors such as food supply that slow down population growth when the population reaches a certain size.